Hello. So it is my pleasure today to present you this talk dealing with the idea of co-optimization. So what I am about to present is based on intervention I made at an industry special session during the conference Innovative Smart Grid Technology, which has been held in Grenoble in October 2023. So what is the idea of co-optimization? So basically it is based on the very obvious settlement that an optimal management and an optimal sizing are interdependent. When I want to assess what is the optimal management of an asset, so for instance, most of what I will present is based on an electrochemical storage, but it could be also adapted to other assets such as grid reinforcement, for instance. So when I want to assess what is the optimal management, so obviously I will have to take into account what is the capacity, the design of a battery, for instance. But likewise, the other way around, if I want to assess what is the optimal sizing to provide a given service, I should also take into account how it will be managed. Because if I suppose that the control of the battery will be done in a very optimal way, in a very clever way, maybe I will be able to provide this service with a given battery capacity. However, if I suppose that the battery will be operated with a very crappy way, I will need a much larger battery. So there is this coupling between an optimal management and an optimal sizing, and it is such a coupling which is a basic idea of a co-optimization approach. So this being said with words, we could try to say the same thing with equations. So we want to maximize something and maximize with the degree of freedom of the design of a system. And the quantity we want to maximize is the difference between how much will be the added value of a system during its entire lifetime minus what is the building cost of such an asset. Okay, but this optimization problem faces at least two kinds of obstacles. So first of all, it is a not so trivial problem because we have two different temporalities. First, we have one decision which is taken once and for all. So it is the design of a system which we have to assume its design during its entire lifetime. And after that, at each instant of the lifetime, we have another decision to take. So it is two different temporalities which are making this problem quite difficult from a complexity point of view. However, maybe the most challenging obstacles that such a co-optimization approach will face is the anticipation of the future, because basically it is science fiction. I am trying to anticipate events during the entire lifetime of an asset, which could be decades. And I am compelled to confess that I don't know what will happen during decades in the future. So I will have to take into account some uncertainties about all the time series, about all the models of how the component will age, will decay, and so on. And all of this cannot be known for sure. But what I know for sure is that all of this incertitude will have huge impacts on the decision, on the results of a co-optimization approach. So it is the motivation of my speech today. It is to highlight this coupling between what is a sizing methodology and what is the expert knowledge of the industrial situation such an asset could be used in, and the fact that we need to know what we don't know in such a way. So to illustrate this, after this introduction I just made, I will introduce a test case, and on this test case I will go on by adding optimal control, then stochastic control, and lifetime and aging effects. And at each step, my point won't be to describe the details of how I could solve an optimal control problem, for instance. On the other hand, I will try to illustrate what is the impact of stochastic control, of forecast errors, for instance, on the final decision. So first of all, the test case. So I've tried to make it as simple as possible, but yet representative of the the challenges that are at stake for such context. So this problem is a virtual power plant associating a wind farm with an electrochemical device, an electrochemical storage device. And this virtual power plant will try to sell its production, so its net production, so the wind production minus what is exchanged, what is stored with the battery, and this resulting power is sold to a market with a fluctuating price. In such a context, the co-optimization problems becomes the following. I try to maximize the quantity with one variable, which is the design, so the energy capacity of my battery, over the entire lifetime from now to the end of life of the battery. What I'm trying to maximize is this utility price times the net power output of the virtual power plant minus a building cost, and I suppose that this building cost will be linear with the capacity of the battery. Of course, all of this depends on many parameters that I have tried to settle in not so dumb ways, but I hope that at this point of my speech you have understand that my main point is to illustrate that all of these values should be put into question in order to assess are they really important, really impactful on the final decision. At this point I should also add that all of this quantity for the purpose of today will be quantified in euros or in dollars, if you wish, but it could also be assessed in order to take into account environmental impacts, for instance, supposing that we would be able to quantify all these terms in carbon equivalence or in primary energy, for instance. Yet, at this point, I should be able to solve this problem with, for instance, the simplest management possible, so the simplest rule of thumb in order to manage my storage. So the simplest bet could be that I will choose a price threshold. If the energy price is higher than this threshold, I will sell and I will discharge the battery, and likewise, if the price is below this threshold, I will store in order to sell in the future. If I suppose that I will manage my battery in such a way, I could draw the following illustration with, in blue, the construction cost of my battery. So obviously it will be linear with the energy capacity of the battery, and it will be negative because it is a costly decision. In red, I have the added value of this battery. So obviously, once again, if my battery is larger, I will have a bigger added value. But what is the most interesting point is the difference between these two quantities. And it is a dark blue line. And of course, if it is below zero, then it is a loss-making decision and should avoid at all costs to build anything in such a context. I will now move to the optimal control section, because I could do something much smarter than just a price threshold. At each time step, what I am really trying to do is to assess what is the storage power which could maximize the utility value, but not just now, anticipating what will happen in the future. So I should have a sliding window from the hour I live in up to an horizon of, let's say, 24 or 48 hours, in order to anticipate the fluctuations of both the production and the price energy in the next 2 days, for instance. And if I do such a thing, then I could have the following illustration as an example. So we have a few days, and at each day we have the fluctuations of the price, which is in blue, and we can note that there is a daily pattern with higher prices and lower prices during the night, for instance. And if I try to manage my battery knowing these prices, anticipating it, and assessing the optimal storage power with this optimal control, we obtain the red curve, and here we can see that each time the price is high, then I will discharge the battery, so it is the negative powers, and when the price is low, I will try to store the wind production in order to sell it later on. All of this, of course, will have consequences on my main figure of the compromise between the utility function and the building cost. And if I do the same figure as before, but assessing that there is this optimal management running, everything is changed. And in this case, the building cost is the same. However, the utility cost is the utility function is much higher, and then I have a profitable decision, and I could assess what should be the optimal storage capacity. But maybe you have noticed something, which is that for this illustration, I have used a time series to simulate, which was the energy prices of 2022. And these energy prices were quite different, to say the least, than anything we have seen before. And if I try to do the same thing, exactly the same simulation with the prices of 2019, and obviously the conclusion will be far different. And with the prices of 2019, the same simulation could answer that we should avoid at all costs to build a storage, for instance. So at this point, not only have we illustrated that there is this coupling between the management and the design of a system, but also we have illustrated that the final result will highly depend on the time series I will use for the simulation. I will now move to my next point, which is stochastic control, because when I was saying in a very simple way that, hey, I should anticipate the future, sorry, but I will not be a fortune teller, and I can't anticipate for sure what will be the price in the next couple of hours, or what will be the wind production in the next couple of days. So, of course, when I will try to anticipate these events, I will make some mistakes, I will do some errors, and it is impossible to maximize really this quantity. The best I can do is to try to maximize the expectation of this quantity. And this expectation, of course, it is based on a forecast. And when we move to forecast, we have really a huge biodiversity. It is kind of a jungle of many different options, many different possibilities to build a forecast. So I will illustrate it on a time sample of energy prices, but we could do the same for the wind production, for instance. So we have a time series, we have the gray line, which is the present, so before it is the past, we know it, and after it is the future and we don't know it, we have to forecast it. The simplest way to have a forecast is to suppose that the future will be what we see today. So what we see now. So it is the persistence of the price during the next events. If I try to be a bit smarter, I could notice that there is a daily pattern, so prices lower during the night and higher during the day, for instance. And I could try to be smarter, saying that tomorrow will be as today, and I will repeat this daily pattern. However, here you can see that I have 7 days. 7 days from Monday to Sunday, and if I try to anticipate the prices of a Sunday, which are obviously lower because there is not so much consumption, if I try to anticipate a Sunday using a Friday, of course I will do some errors. So I could try to be even smarter, trying some modeling approach of time series, and here we could go for our favorite flavors of machine learning, from time series modeling with Sarimar, for instance, to neural networks and so on. But for any of these flavors of machine learning, we could have the same drawbacks, which could be that maybe we could have some forecast of really good quality sometimes, but sometimes also we could have some huge errors, even more when the forecast horizons is longer. And if I try to be even smarter, I could just call a friend. Because some meteorologists, for instance, do really good forecast of what could be the wind, what could be the solar irradiance if I had a PV plant, for instance. So if I want to have the best quality forecast, the simplest decision that I should do is to just call a provider of a forecast, which will give me a forecast which most of the time will be of a very good quality, but my work in such a condition would be to learn what could be the errors of this input forecast. And so the modeling of the forecast errors will be should be the task I will spend efforts on. And for the purpose of readability of the previous figures, I have drawn only one trajectory for the forecast, but it is stochastic forecast by definition. So if I want to have a stochastic forecast, I can't just have one scenario. I should have an ensemble forecast which is made of a set of scenarios. And then with this set of scenarios, it will become my choice as the owner or operator of the battery to decide what is my risk policy. Am I risk neutral? So let's say I will want to maximize the average expected gain, or maybe I am really risk averse and I think that all the natural events will play against me, but I want to have a kind of a minimal gain in the worst possible conditions. So this is a risk policy question, which obviously is outside the scope of just a co-optimization problem. It is an input choice that I have to take into account in order to solve my co-optimization problem. And of course, all of this will have consequences on our co-optimization results, of course. So once again, the same figure, but this time I will draw a comparison between what could be my decision if I suppose that I will have a 100% accurate forecast. So let's say that I know a really good fortune teller, and in blue, what could happen if I do the really simplest possible way, the persistent forecast. So of course, not only you can see that the output will be absolutely different, so I will go from something like 60 to 70 megawatt hour for the optimal design to something maybe 40, 30 megawatt hours. So this is one point, but not only the optimal decision will not be the same, but the expected added value of the operation would be much smaller. So it is from something which is 10 to nearly zero, barely profitable operation. And if I do the same, supposing that I have a very good friend which will provide me with a forecast, so let's, for instance, a meteorologist, then I could be close or not too far from a deterministic performance. So the conclusion for a co-optimization approach is, if I want to be able to solve my co-optimization problem in a relevant way, I should also take into account not only the time series I will simulate all of this on, but I should have in mind what will be the forecast of the time series. So if I want to sign a contract with an external provider of forecast, for instance, I should ask him, could you provide me the forecast you've made in the past in order for me to assess what will be the quality of your forecast, so that I could assess what will be my optimal design. My next and last point will be how to take into account the lifetime fluctuations and agings. Because up to now, I have made the assumption that my battery will last for 10 years. And I can justify it, because I don't know it for sure. But all I know is that it will have a huge impact on all my decisions, because if the lifetime is not the same, well, the capex cost will still be the same, but the utility function will be much reduced, because it is not on the same duration that I will operate my system on. So, as an illustration, what happens if I move from 10 years to 8 years of a lifetime? But either 10 or 8 years, none of them are true, because the same goes for batteries as for human beings. My lifetime will it is not a fixed value which it could be known in advance, but it is a consequence of all the events I will go through. And so if I want to take that into account, I should modify my co-optimization problem, saying that there is a new term, which is how much damage I will do to my battery with each and every decision. So each time I will exchange some power, I will create a very small damage to the battery, and in the end, when I will add all of this damage, it will give us the state of health of our batteries. And if this state of health reaches 0, then the battery is considered as dead, and it is the end of the lifetime. So it adds a new complexity to this problem, but the real complexity is what could be this aging model in itself. Because when I want to modelize how a battery could decay, aging models go from things really simple to things which are endless complex, because it is really a very difficult topic. But once again, I am not here to close this issue once and for all. What I am just about to say is to illustrate how this could have an impact on a co-optimization approach. And to this purpose, I will just consider the simplest possible aging model, so which is that for a battery, I have a given amount of cycles this battery could undergo. So for instance, 10,000 cycles during this whole life. And once it has done its 10,000 cycles, the battery is considered as dead. And so for a battery of a given capacity, the capacity times 10,000 cycles will give us how much energy it could exchange during its whole lifetime. So it is a damage model based on exchange energy. And if I take into account this quite simple model into my co-optimization problem, then all my results are shifted. And it is a new dark blue curve. And you can see that the optimal design for this dark blue curve is much higher than before. Why is it? But just because for smaller batteries, they are small. So they can't exchange that much energy during their lifetime because their capacity is small. So for smaller batteries, they won't be able to last for 10 years or to 8 years. They will have a very short lifetime just because their exchangeable energy will be reached very soon. And if I want to have a battery which could last for years, I will have to move to bigger batteries. So once again, I am not here to close this question once and for all, because aging models could be really complex, but I'm not here also to avoid this issue, because it will have consequences on our decision of design. So we have to make a choice. It is mandatory to have this choice as soon as during the design phase, and all we have to assume is to know the consequences of such a choice. So I will now come to my conclusion. The co-optimization is a really powerful methodology because it gives us the keys to assess what is the best design over the entire lifetime. And so not only it is a very appealing methodology and powerful, but also it's becoming more and more mature from just the computational point of view. However, even if it is kind of mature and ready to use, when I want to use that in the real world, the end result of a co-optimization will be very highly dependent on all the input data, and it is what I've tried to illustrate. So the optimal management will call for what time series are you simulating on. The stochastic management will require the forecast that you will be using during the lifetime of your batteries, and of course the lifetime is not a fixed value but a consequences of an aging model. And all of this cannot be, it is a bunch of choices that cannot be made by just one person with his computer, because it requires expert knowledge and communication between many different persons. I have the provider of the forecast, I have the manufacturer of the battery, and I need to regroup all the knowledge of all of these people in order to have a really even co-optimization approach. And so the final take-home message that I have here is that, of course, when we know something for sure, we can take it into account into our co-optimization methodology. But even if we do our best, there will still be things that either cannot be measured or cannot be known for sure. And all the best we could do is to have reasonable or explainable assumption or sensitivity analysis in order to assess what will be the consequences of all this input data that we don't know for sure. And that's all for me, and I thank you for your attention.